The Doppler effect. You'll all be familiar with this from the distinctive tone change as a car goes past you, a higher pitch as it approaches, a lower pitch as it goes away, something like this. Now, this effect is also seen in water waves and light waves. So first I'm going to look in more detail using water waves. Here we have a duck on a pond swimming to the left and producing ripples, and we get this sort of an effect. If that has taken 1 second, this point here has had 1, 2, 3, 4, 5 waves pass it, giving a frequency of 5 waves in 1 second, or 5 Hertz. This point has had 2 waves pass in 1 second, giving a frequency of 2 Hertz. So just like with the car, we have a higher frequency as the duck approaches, a lower frequency as the duck moves away. Now to look at the effect on light. Here we have a line absorption spectrum from a local star within the Milky Way galaxy, or observed in the lab. If we look at the same absorption spectrum, but now from a local galaxy somewhere away from the Milky Way, we see that the lines have been moved across to the right, towards the red end of the spectrum. We say the light is redshifted as the wavelength of the light has increased. This can be explained by the local galaxy moving away from us. If we observe light from a distant galaxy, we see that the lines are even further shifted across to the red end, even more redshift, suggesting that the distant galaxy is moving away from us faster than the local galaxy was. As we're considering the recession speed of galaxies, it's light we're interested in, but for simplicity I'm going to look in a little bit more detail at the duck on the water. We know that wave speed is equal to frequency multiplied by wavelength. Here I'm going to use the symbol c. This generally applies to electromagnetic radiation, but it also allows us to distinguish between the speed of the waves and the speed of the object. In 1 second, the frequency tells us how many waves have been produced, and in this time the source will have moved a distance equal to the magnitude of the speed v. Distance is equal to speed times time, so in a time of 1 second we move a distance equal to the magnitude of that speed. So the source has moved a distance v to the left, the waves have moved a distance c to the right. So the wavelength of these waves is the distance available to them, v plus c, over the number of waves produced, f. The change in wavelength, which I'll call delta lambda, is equal to the new wavelength, which we've found here, minus the wavelength if the source had been stationary, which is given by c over f, a rearrangement of the wave equation. We can now simplify this expression to get the change in wavelength is equal to the speed of the object over the frequency of the waves. We also know that frequency is equal to wave speed over wavelength, and so we can substitute in here to get that the change in wavelength is equal to the speed of the object multiplied by the original wavelength over the wave speed. Rearranging again, we get the change in wavelength over the original wavelength is equal to the speed of the object over the wave speed. We can also write that the change in frequency over the original frequency is equal to the speed of the object over the wave speed, or the change in wavelength over the wavelength. But this only applies if the speed is much less than the speed of the waves. This will apply in any A-level problems. Let's look at an example. The red hydrogen line at 656 nanometers is observed in a distant galaxy, but with a wavelength of 672 nanometers. Calculate the velocity of the galaxy relative to Earth. Is it moving towards us or away from us? Well, we know that delta lambda over lambda is equal to source velocity over wave velocity, and so we can rearrange to find v is equal to c delta lambda over lambda. Putting in the numbers, c is 3 times 10 to the 8 meters per second. The changing wavelength is just the difference between the two wavelengths given. Don't forget it's nanometers, so it's times 10 to the minus 9. And the wavelength we want to use is the stationary wavelength of 656 nanometers. This gives a recession velocity of 7.3 times 10 to the 6 meters per second. It's very easy in a question like this, in an exam situation, to forget to do this last part of the question, which can lose a valuable mark. So, is it moving towards us or away from us? It's an increase in wavelength. The light has been redshifted, so the galaxy is receding. The wavelength has increased. Now, the term redshift can be a little ambiguous. Here I've laid out the members of the electromagnetic spectrum in order, with the visible part red, orange, yellow, green, blue, indigo, violet. If a light source has moved from, say, the blue to the orange, it clearly has moved towards the red, and the term redshift is fine. But we'd also use the term for a microwave that would be this wavelength moving to a longer wavelength. In this case it's actually moved away from the red, but we still use the term redshift. So we always use the expression redshifted when the wavelength has increased due to recession, the source moving away. Shortened wavelengths due to approach are known as blue shifted. Here we have a rotating star being observed here, and at this point the light from the approaching side would be blue shifted, as this side of the star is actually moving towards the observer, whereas light from this side would be red shifted. This side is moving away from the observer. Observations like this allow the rotation speed of a star to be calculated. The rotation speed of galaxies can be found in the same way, but these speeds are found to be far higher than would be expected for the known mass of the galaxy. It seems there is extra mass within the galaxy for which we have no other evidence. This has become known as dark matter and is the subject of much research.